Assalamu alaikum. Today we are going to discuss about supervised learning and we will explore an algorithm that is called K-nearest neighbors. In supervised learning, we have label instances, which means we have the data and we have the associated labels with the data as well. And we need to predict a data element to some specified category. This is called classification. A classification algorithm takes a dataset that contains both features and the labels and then predicts a category or a class. For example, if you want to predict if an email is spam or not, or if you want to predict if a loan should be approved or not. There are different classification algorithms such as k-nearest neighbors, knife Bayes, decision tree, support vector machines, neural networks, and so many others. In this lecture, we will explore k-nearest neighbors. KNN's mechanism is similar to k-means algorithm, but don't confuse it with k-means. K-means is unsupervised learning algorithm, while k-nearest neighbor is a classifier, that is a supervised learning algorithm. So how does KNN works? For a given instance T, get the top k dataset instances that are nearest or closest to that instance T, and then select a reasonable distance. Usually we use Euclidean distance or Manhattan distance. Then inspect the category of these k instances. Choose the category C that represents the most instances. And then we conclude or predict that the new instance T belongs to the category C. For example, we want to take decision on scholarship applications based on the following features. Number 1, the household income. Number 2, the number of siblings in the family. And number 3, high school grades. So the intuition is that the award should be given to the high performance and to those with financial needs. So here is the formula of the distance matrix, that is Euclidean distance, in which we take the difference of the two values and then take the squares and then sum them up, and at the end we take the square root. The solution behind this is that the similar samples should be closer to each other. The Euclidean distance formula has an assumption that the different dimensions are comparable. Features that span a wider range affect their distance values more than the features with limited ranges. So it is important to first scale the data and then apply this algorithm. Let's take our previous example. Suppose the household income was in thousands of rupees and the grades were given between the range of 70 to 200. So there is a difference between the scales of the two features. There is one more important thing. We can represent the numerical data, but what if we have the categorical data or Boolean data? For example, if you have yes or no, or if we have education, if we have gender or colors. So how would we represent this data and how do we find the distances between them? Comes the encoding. So for Boolean values, we can convert it into 0 and 1. For the categorical values, we can numerically encode them as, for example, we have education, then we can encode it into 1, 2, 3, and 4. Similarly, we can encode different values to numerical. Before proceeding with the k-nearest neighbors, we need to first pre-process the data. We need to convert the non-numerical values to numerical values. We also need to see if there are disparity between the ranges of different attributes. KNN variations. So the important thing is the value of k. Larger the k increases the confidence in prediction. Note that if k is too large, the CN may be skewed. K nearest neighbor is based on the majority decision. So plain majority may unfairly skew the decision. We can use weighted evaluation to assign higher weights to the closest neighbors. We can also try with different distance matrices. For example, we have Manhattan distance. We can calculate the cosine similarity. We can use Jacquard index. And there are so many others as well. The time complexity of k nearest neighbors algorithm can be significant, particularly in large datasets. During the training phase, the KNN has a time complexity of order order of 1 because it simply stores the data points. However, the real computational comes during the prediction phase where the time complexity is order of m raised to the power n. For each query point where m is the number of training samples and n is the number of features or the dimensions. This is because KNN must compare the distance between the query points and every training point. Efficient data structure like KD trees or ball trees can be used to reduce the complexity in low dimensional space, but they become less effective as dimensionality increases. Let's start to understand the k-nearest neighbors with an example. So here we have a data set in which we have a label that is fruit and we have two features, size in centimeters and weight in grams. The fruit feature is actually the label and it has two distinct classes, apple and orange. So what we need to do, we need to classify a new data point. If we have a new fruit and we know the size and weight of the fruit, we will try to classify it in either of the two categories, apple or orange. So let's suppose we have a new fruit with a size of 5.5 centimeter and weight of 190 grams, and we want to predict is whether it is an apple or an orange. Step 1 is to define the value of k. So first we will decide what should be the value of k. Let's take k equals to 3, which means we will look at the three nearest neighbors to classify the new data point. That is why the name of this algorithm is k nearest neighbors, because we look at the k nearest points around the new data point to classify it in either of the categories. So the next step is to calculate the distance between the new data point and all of the other data points. We will use the Euclidean distance. So we will calculate the distance between all of the data points and the new fruit that has a size of 5.5 centimeter and weight of 190 grams. So the formula of Euclidean distance is x2 minus x1 square plus y2 minus y1 square and then under root. Since we have only two features x and y, so we have only two features in the formula. Suppose we have one more feature z, then the formula will include one more distance, that is z2 minus z1. So here is our data set and we will calculate the distance between the new fruit and the first instance in our data set, that is apple, with the size of 3 centimeter and weight of 150 grams. So how we will calculate the distance between them? So we will take the difference. So the new fruit has size of 5.5 centimeter and our first instance has size of 3. So 5.5 minus 3, and the new fruit has the weight of 190 grams and the first fruit in our data set has the weight of 150 grams. So we will take the difference and then we will take the squares and at the end we will take the square root. So we will have the first value, that is 40.06. Similarly, we will calculate the distance of the new fruit with all of the other data points. So we have the values for second fruit, we have 20, for third we have 10, then 20, then 30, and then 15. So now we have calculated the distance between the new fruit and all of the other data points. Now we will match to which class the fruit has the lowest distance. Now the step is to find the nearest neighbors. So we will select three instances from our dataset that has the minimum distance from the new fruit. So the three instances are as follows: orange 10, orange 15.03, and apple 20.03. So we have shortlisted the three closest points to the new data point. Now we can see that uh, we will actually make the majority voting. So two are orange and one is apple. So out of the three, we have two oranges and one apple. Since the majority of the nearest neighbors are oranges, we will predict that the new fruit is an orange. So the final prediction is that the new fruit with size 5.5 centimeter and weight of 190 gram is predicted to be an orange based on the KNN algorithm with K equals to 3. Let's discuss some of the challenges that are associated with K nearest neighbors. The first one is the computational complexity, as we already discussed. KNN can be computationally expensive, especially with large datasets, because it requires calculating the distance between the query instance and all other instances in the dataset. The second one is storage requirements. KNN is a lazy learner. It means it stores the entire dataset. This results in high memory usage, particularly with the large datasets. Next is it is sensitive to irrelevant features. It does not automatically differentiate between the importance and relevance between the features. So, irrelevant or noisy features can negatively impact the performance of the model. There is one more important thing, and the major drawback is there is no training phase. Since KNN does not build a model during the training phase, there is no opportunity for optimization before making predictions. KNN is sensitive to feature scaling. The algorithm is sensitive to scale of the features. If the features have different scales, those with larger ranges will dominate the distance calculation unless normalization is applied. Curse of dimensionality. KNN suffers from the curse of dimensionality. In high dimensional space, the distances between the points tends to become less meaningful, reducing the algorithm's accuracy and effectiveness. And the last one is choosing the optimal value of k. Determining the optimal value of k can be challenging. A small k might lead to overfitting, while a large k could result in underfitting. In conclusion, the k nearest neighbors is a simple algorithm known for its ease of implementation and flexibility. It's a non-parametric and instance-based algorithm, which means it makes prediction based on the proximity of data points without making strong assumptions about the data underlying distributions. However, KNN can become computationally expensive for large datasets and high dimensional spaces, and its performance can be sensitive to the choice of k and a distance metric. That's all for today, and we will meet in the next lecture. Till then, Allah Hafiz.